forget. All right. All right, so any questions about the course so far? Concerns?
Are you going to do any like study guide type assignments before our exams?
No study guide. We will have a review session at least before the first exam. I don't remember if I'm doing them for all the other ones. But Ace, do you have your passport?
I think that's it. I don't know how to, what's the passport?
So it's through what you said you can access it through Canvas, is that right?
Yes.
So go on Canvas if you can access that. Sorry to make a big deal out of it, but
No, I mean,
I'm not allowed to.
curious about it.
Yeah.
I'm trying to help people, so.
Yeah.
There should be like a tab on your dashboard that says like COVID-19. Yeah, go to modules. So go to assignments. And then it should be a link called Chart and Health Track.
And I mean, for the rest of y'all, I trust that you're not coming to class feeling sick, but the administration's made it very clear that I have to make sure that everybody's in compliance with all of this before we get started. So, all right. So today, we are finally getting started with some calculation. Starting to get ready for actual statistics here. If I can get this going, why aren't you working? All right. What did we learn last time? Mm-hmm. Yes, exactly. So if you get your mean for a set of scores, and then you add a constant to every one of those values, that's the same as adding that constant to the mean itself. Right? So what you do to every score, you are doing to that mean. What else did we learn? Yeah. Yeah. Okay. So what else did we learn? We learned the median. What else? I think I heard somebody say it. And the mode. Yes. What else? Mean, median, mode. Yes. Perfect. Sorry about those on the chat. I'm trying to get this. Good Lord. Come on now. Trying to get y'all dragged to the right area here. Bear with me just a second. Yes, so what is the mode?
It's the score that appears most often.
Yes, it's a score that appears most often. All right, this isn't working. We're just going to leave y'all up there. All right, and so when white, we want to use the mode rather than the mean.
For like favorite color and like the number of people that have the same favorite color or something like that.
Yeah, exactly. So we're going to use the mode anytime we've got like nominal data, right? You want to be using it for what's your favorite color? Or like what's your favorite restaurant, things like that. So wherein it doesn't make sense to actually have a mean, you would want to use the mode. And then the median was the third thing. What's the median? It's what? Yeah, it's the middle of all the numbers, right? So when you rank order those numbers from smallest to biggest, it is that middle point. What happens if you have an even number of numbers? Yeah, you find the mean of those two middle numbers. Exactly. All right, what else did we learn? Yes, and so when you have a symmetrical distribution, where are all those in relation to one another? Didn't need to do that. What about when you've got a positive skew? And so you mean from the center, mode, median, mean, means out in the tail? Yes, exactly. Perfect. All right, questions about what we covered last time? Everyone feels pretty good about it? Straightforward? Awesome. I don't know why this is being so finicky today. All right, here's your fun fact of the day. Oh, go ahead.
Are we gonna have to know precise median?
So I suspect you're referring to based off of the distribution or the number of values that fall on that median value. So calculating like decimal point.
Yeah, the book
Yeah.
gives like an equation to figure out the
Mhm.
precise.
Don't worry about that. No, I've never seen anybody do that outside of this book. So, all right. Yeah, so fun fact of the day, Amelia Earhart and Eleanor Roosevelt once snuck out, I guess sneaked out is the correct conjugation, of the White House event, commandeered an airplane, and went on a joyride to Baltimore. Let me try one more thing here with the chat. I'm trying to get it so not everybody sees the chat. That way if you send me, there we go. Perfect. All right. Whew. I think I need a weekend. All right, so today we're talking about variability. When we talked about measures of central tendency last time, we were talking about kind of a description of the data to tell us what was kind of the most representative point of that data. But that alone isn't going to give us the best understanding of the data itself, right? So we want to get the variability. We want to see how spread out scores are. So if we have two distributions here, that's distribution 1, and that's distribution 2. And this is purely just a frequency on the y-axis. You can see that both of these distributions are going to have the same mean, right? They're also likely going to have the same median and the same mode. But they're obviously different distributions, right? In this lower distribution down here, at the really low end and at the really high end, you have almost nobody in those categories or with those scores. But in this top distribution, you have a lot more people at the low end and at the high end. And so variability is going to allow us to see, okay, what is this actual spread of the data? How flat is the curve? Right? At the beginning of the coronavirus, all we heard was flatten the curve, right? So that is kind of building off of this principle of variability. We wanted to greatly increase, essentially, the length across the time for a certain number of people to get sick, right? Because we didn't want this to happen, because now that means everybody's getting sick in this little period of time. We wanted it to look more like that. And so the same number of people might get sick, but now our hospitals can keep up with that number of people getting sick, and we don't have to start triaging care like they did in, for example, Italy. And so again, the central tendency is just describing that central point of the distribution. And the variability is describing how spread out are the scores around that central point. have your central points there. You can see this is a little spread. Here, this is a much bigger spread. And that's essentially what we're going to be calculating today. So variability as a descriptive statistic, like I said, is giving you an understanding of essentially how much differentiation is there in our sample. I could collect everybody's height, and we could have a really low variability. So maybe I wanted to see, okay, what's the difference in height between basketball players and gymnasts, right? There's probably going to be a fair amount of variability in basketball players because you're going to have the guards who can be 5.5, a little taller, all the way up to the Yao Mings who are, what, 7-something? A lot of variability. For most gymnasts, though, it seems to be the case. You were the gymnast, right? Yes. Most gymnasts, it seems to be the case that they're kind of hovering around the low 5 foot, right? And so there's probably not going to be much variability just because of the demands on the body in gymnastics. And so this allows us to see, okay, what do we now know and what can we kind of determine about the population or the sample based off of that variability? But we also use variability in almost all the inferential statistics we're going to be going over this semester. So the equation you're going to be learning today, you're going to be using for just about every subsequent inferential statistic equation that you learn throughout the semester. And the reason we use it is because it allows us some degree of certainty about how representative a data point is of the population. So again, drawing another distribution here. This distribution on the left, if I pick a data point just randomly from here, it's a lot more likely that the data point I pick is fairly representative of this smaller spread in there than a data point I pick from here, right? Because there's more data out in the tails on this right-hand side graph, such that I can just pick randomly and maybe not get a sample or a participant that is in fact representative. So said another way, when the population variability is small, any individual score or sample will provide a good representation of the entire set. When the variability is large, on the other hand, when you're sampling from that population, if that population has a large variability, the possibility of me getting 1 or 2 extreme scores in the tails is higher, and that can subsequently distort our picture of the general population. Let's say this is our population graph, and I want to pull 10 people out from this. This is just a frequency. So it's more likely, or excuse me, the higher this curve is, the more likely it is I'm going to pull somebody from that area of the graph, right? And so I'm likely to get people from all over, but a lot more from this kind of middle in here. If I've got a really flat graph, though, there are a lot more people, or there's a greater probability that I'm going to be getting some of these extreme scores. So what we have here on the left-hand side is two different groups, right? Two different populations, two different treatments, two different samples. Think about it however you want to. The white boxes over here represent treatment 1 with a mean of 35. On the right-hand side, represent treatment 2 with a mean of 40. And you can see that pulling anyone from, let's say, treatment 2 gives you a fairly good indication about what are the other scores in treatment 2. Right? You can see that there is a pretty clear delineation between these two groups. On the right-hand side, however, you still have the same means, right? Still mean of 35, mean of 40. But you can see it's a little bit less of a clear picture about differences. All right, so treatment 2 is still higher in the mean. But in reality, if you took this one away, it looks like there's not really any difference, right? This is an extreme score with a big distribution. And this is the principle upon which all of these mean differences tests that we're going to be doing this semester is built off of. We're going to be looking at the mean values that we have. So what is that average value? And then we're going to say, based off of that average value and the variability, so is it a really tight group here, or is it a really spread out group, like over here? What's the probability that that mean difference you have here, so this 5-unit difference, is due to chance, or is due to the fact that there is a real difference in the world? It's a lot more likely that it's due to chance. Exactly. Yes. Other questions so far? All right. So we can measure variability with 3 things primarily, and you're going to see standard deviation, variance, sum of squares are going to be related to each other, so grouping those together. But the range, the interquartile range, and then the standard deviation and variance. So the range is just that total distance covered from the lowest point to the highest point. All right, if I were to get everybody's ages in here, so if somebody's 19, and I'm probably the oldest, so it'd be 19 to 30 would be our range, or it would be a 12-unit range. So you're taking the high minus the low, using these real limits. So again, somebody give me a real quick recap. What is a real limit for data? Yeah. Exactly. Yeah. So just think about it in terms of grades, right? My cutoff, my real limit to give you an A is 89.5 because I'm rounding that up to a 90, right? So that's that real limit. So you're taking the real limit. So if we have a range from 10 to 25, the actual real limits are going to be 25.5 and 9.5. So that range would just be 16. Or an easier way to calculate it is just high minus low plus 1. Easy peasy. Yes?
Do you have a range that is done differently for a continuous variable versus the discrete variable? Or should it be the same?
So give me an example of a discrete variable that you would want the range on. Okay, yeah, so while you're right, that is absolutely a discrete variable, the nature of that, of number of a class would be like a quantification, a single unit quantification. There wouldn't be a range in there. Does that make sense? So if we were to count the number of people in this class, 15 or so, that wouldn't be a range, so to speak. You could have a potential range, let's say, if we counted this class and every other class at this time on UH, but that would be a continuous. Okay, yeah. I mean, I guess if your question is when you only have whole units, rather than, okay, yes, if you only have whole units, yeah, it's the same way. It's the same approach. Yeah. Sorry, I think I misunderstood your question initially. The interquartile range is just the distance covered by the middle 50% of the distribution. So whereas the typical range would be from tail to tail, your interquartile range would be, okay, at what point is the 25th percentile? At what point is the 75th percentile? You've got your mean in there. And so this would be the IQR, as is frequently abbreviated, interquartile range. And you can see how the interquartile range is giving you a little bit more information, right? The range is just telling you from low to high, but it's not telling you, okay, what's the spread in there? The interquartile range is giving you essentially how flat is this middle part of the curve. Okay, yeah. So you have the mean here, the middle, and this is quartile 1, this is quartile 3. And so essentially just think of this as broken up into 3 quarters.
Okay. So it's going from quartile 1 to quartile 3.
Exactly, yes. And it's broken into quarters not by what's on the x-axis, but by the number of people in that. So if you had 100 people in your distribution, this would be person 25, this would be person 75, and the difference between their scores would be that interquartile range. For an interquartile range, yes.
Okay.
Yes, so the root of that is the quart, which is 4. You can have quintile ranges. I mean, you can split it up, but for an interquartile range, it'll be 4.
Okay. I just didn't know if it was like randomly selected.
Ah, yes. No. Good question. Nope, 25 and 75. Other questions? Awesome. So again, just to represent here, you have the bottom 25%, you have the top 25%, or you have the 25th person, you have the 75th person, and the difference between their scores represented here, is that inner quartile range. So you could see how you could have the same normal range going from 2 to 11, but you could change that inner quartile range just based off of where these values fall on that x-axis. Now we get to the fun stuff. Standard deviations. So a standard deviation, like its name would suggest, is that standard deviation of a single value from the mean. What is the average distance between a score and the mean? So again, if we have a distribution, here is our mean. The standard deviation is saying, okay, we have this point, how far is that away from that mean? We have this point, how far is that away from the mean? We have this point, and all we're doing is averaging those distances. I know there's a lot of text, but we'll get through it here. To find the standard deviation, and we're going to go over an example here. You're going to first compute the deviation, or the distance from the mean, for every score. Once you have that deviation, that difference between the score and the mean, for every score, for every x, you're then going to square that deviation. You're going to square every one of those deviations. You then calculate the mean of those squared deviations. So for a population, this involves summing the squared deviations. So what we did in 2, we're adding all of those together now. And if this feels overwhelming, don't worry, we're going to do an example in just a second, and I think it'll make more sense. And then dividing by n. And what is n again? Or the number of people in that population. Yep. The resulting value is called the variance. Sometimes also called mean square. And that's measuring the average squared distance from the mean. So when we've got the population, we divide it by n to get the mean. When we've got a sample, we're dividing it by n minus 1. And we call this new number our degrees of freedom. Sounds like a very patriotic term. But the degrees of freedom is essentially giving us a fudge factor. Right? So we have our population. We have the entire group of UAH students. We want to pull a sample out from that. So we get 30 people. That sample, we're hoping, is representative of the population. But to give us a little bit more uncertainty, to add a little bit to that variance, we're going to take those 30 people, subtract by 1 to get 29. And one of the reasons we do this is for a reason we're all kind of intuitively familiar with, right? So again, going back to that coin flipping example, is it more likely to get 100% heads when you flip the coin twice or when you flip the coin 50 times? Twice, right? Yeah, it's a lot more likely it just comes up head back-to-back times than it comes up head 50 times in a row. And so what this is saying is when you've got a lower number of people, when you're flipping the coin only twice, we need to have a much bigger variability than when you're flipping the coin 50 times, right? Subtracting by 1 is going to make a big difference when you've only got 5 people. It's going to make a much bigger difference than when you've got 50 people subtracting 1. So that's the conceptual reason we are doing this in -1. And then once we have our variance, we're taking the square root of that to get that standard deviation. So again, we squared everything to get the variance, and we squared it all, because as you'll see here, if you don't square it, it's going to come out to 0 because it's just the average deviation. So squaring it is essentially giving us that absolute value, but it's squared. And then getting that standard deviation, we're taking the square root of it. So just to give you a little flow chart, first you're going to find the deviation, the distance from the mean. You're then going to square each deviation. You're then going to find the average of those squared deviations, dividing either by n for the population or n minus 1 for the sample. You then take the square root of that variance to get the standard deviation. And that standard deviation is, again, just that standard distance from the mean. There is, and we're about to go over it in just a second. All right. So you can represent the sum of squares. Let's walk through each one of these things. What does sigma mean? Sum. Yep. So we're doing the sum of everything in this parenthesis. What is x? Yeah, whatever your individual data point is. I forget what this Greek letter is. Mu?
Yeah, mu.
Yeah, okay. Mu. Minus mu, and what does mu represent? The mean. Yep. And then we are squaring all of that. To get that variance, we're taking the average of everything we did in that sum of squares. And I actually don't like this equation. I'll show you another equation in like 2 slides here that I think will be easier for you. But this is showing you conceptually what I just told you. All right, so is this variance the population variance or the sample variance? How do you know? Okay, yes, but how else would you know? Exactly, you're dividing just by n, right? So this is the population variance. And then, once you get that variance, you take that square root of it, and that gives you the standard deviation. All right, so let's throw all that into a table here and actually perform this. All right, so over here, this X column, that's every one of our data points, right? That's all the data points that we have right here. So the first thing we have to do is find what is our average, our mean. All right, so we sum up X, also represented sigma X, right? Sum of all of these values here. We get 60. We have the count for number of data points, in this case 10, which gives us a mean of 6. All right, so now we have our mean. So we come over to the second column here, and the second column is, yes, sorry, I missed y'all's comments there. You're absolutely right. And so we have our mean of 6. So this is saying for every X, subtract 6. So 7 minus 6, 1, 8 minus 6, 2, 2, 1, negative 3, negative 5, etc. And then we square every one of these values before we add them up. Right? Because if we just added them up now, they would all add up to 0. Right? Because this is just the deviation from the mean. And the mean's going to be right in the middle of it. Right? So we take 1, we square it, we get 1. Take 2, we square it, we get 4. 4, 1, 9, 25, etc. So now we add all of those up, and we get 66 here. This 66 is the sum of squares, right? It's the sum because we've added it all up, and squares because it's the squared deviation values. Sum of squares. So we use this equation up there to get that 66. We now want to find the variance. So to find that variance, we just take that 66 that we had from the sum of squares, and we are dividing it by n in this case because we've got a population. So 66 divided by 10 gives us a variance of 6.6. And what's the relationship between variance and standard deviation again? The standard deviation is the square root of the variance. Yes, the variance is the standard deviation squared. So we have our 6.6. We take the square root of the variance. Gives us 2.57. And so this is telling us what is that average distance from each point in our sample, or in our population rather, to that mean. So on average, every data point is 2.57 units away from that mean.
also look at it as the mean of deviations.
Say that one more time, the mean of deviations. Yes, but be careful because you're not just taking the mean of the deviations that we initially calculated, because that would give you 0. And so it's the mean of the absolute difference, or excuse me, yes. It's the mean of the absolute value of the distance from it. So I think I actually got these slides out of order. Let's go to this one first, then we'll go back. You could also calculate the sum of squares with this equation. And this is nicer because it requires kind of one less step for you. So ignore everything below this first line. What is this first indicator telling us to do?
Out of all the numbers.
Almost. It's saying square every x you have, every data point, and then add all of those up. What about this over here?
Add up every score and then square it.
Yes. Yeah, so you're adding up every x, and then you're squaring it, and then you're dividing by n. So that equation again, sum of x squared minus the sum of x, squaring that, over n. So what are we doing? We are squaring every x value, every data point we have. We're squaring it. 7 squared, 49, 64, etc. We're going to add up all of those to give us that sum of x squared. Right? So this first thing, that sum of x squared, is 426. We're now going to subtract the sum of x, which will be squared. So the sum of x, right here, is 60. So we're going to subtract 60 squared divided by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10. So we go back to this page here. You see where we got that 426 from. You see where we got the 60 from and the 10. So now the order of operations says that we need to square the 60 first. 60 times 60 is 3,600. Continuing on with the order of operations, we need to do everything in the parentheses here. So 3,600 divided by 10 gives us 360. So now we're going to take that sum of x squared, that 426, and subtract that 360. And that, once again, gives us 66. Right? Same data point we were using before, same answer, just a different way of going about it. And you can see how this one may be a little bit easier because it's not requiring that you subtract the mean from every individual data point you have. Right? You can just add up the columns and square each one of them. It gets a little bit easier. So again, that sum of squares is 66. Divided by 10, 6.6. That 6.6 is the variance. Take the square root of that. Once again, 2.57. Questions on this so far? So standard deviation will certainly be on it. I don't know if you're going to be calculating it by hand or not. Other questions?
Do we have to go through that extra step of subtracting like the extra square each time? Because when I calculated it, I made a table of x minus the average, and then I just made another column of that number squared, and then I just added all those up. I mean, like, do we have to? I'm saying, is that an okay way to do it every time?
Yeah, you can absolutely do that every time. So that was the first way I showed it. And so you can do that every time if you prefer to do that. A lot of people tend to find this approach that we just went over with this equation right here as being easier, but you can absolutely do it that first way we did it if you want to.
Thanks.
Yep. Other questions? Take the square root of the variance. Yes. Yep. Yeah. So as you can see, with the same data, those two different equations, we get the exact same. Because they're doing conceptually the same thing. They're just doing it in a slightly different way. Cool. All right. Let's have y'all practice. So take these scores up here and then find the standard deviation. Don't worry about the rest of this because we're running a little short on time with what I want to cover. So just find the standard deviation for these data points.
two decimal places, like 2 places?
Yeah, 2, 1. For the example specified. $93 more seconds. All right, we want to find the standard deviation. What do we have to do first? What do we have to find first to get the standard deviation? Okay, so we can find the mean. But I'm thinking in terms of sum of squares, variance, and standard deviation. Yeah. Okay, so we'll go to our equation here, right? So sum of x squared minus the sum of x, close paren, squared over n. What does this give us? What is this the equation for? Yeah, sum of squares, right? Now, how do we get from the sum of squares to the standard deviation?
So we square all of those numbers that you have there, and we add those up.
Well, so let's pretend we've already got our sum of squares value from this equation.
So then we divide sum of squares by 10.
Exactly, yes. So we've got our sum of squares with that equation. Our variance is just the sum of squares divided by n. And then how do we get the standard deviation from there? The square root, exactly. So the standard deviation equals the square root of that variance. All right, so now let's go ahead and do this. One second here. I didn't mean to stop sharing the screen. All right, so I'm doing it instead of, whoopsies. All right, let's try that again. I don't think it's going to throw me into a feedback loop. All right, so we've got our x. Stop doing that. We're going to take every x and square it. I hope that's not too annoying for y'all on Zoom. I don't know why it's not ignored or not doing that. All right. I should have this mic turned off. Yep. And this should be coming off of, let's see. Okay, it's not too bad. Perfect. All right, so we've got our x, and I'm just going to talk over this like I'm giving a speech to an arena. So let's put in every one of our values. 3, 1, 3, 1, 2, 4, 4, 2, 2, 3, whoopsies. All right. I hate technology sometimes. All right, so we're going to square every one of our x values. So I'm just going to square that. And now I can get the sum of all of these. So this is going to be my, search here. This is sum of x squared right there. And this will just be my sum of x. All right, so now if I go back to 140 or 44. All right, so our sum of x squared was 140. Our sum of x was 44. So if we take our equation, the sum of x squared, 140, minus 44 squared, and we had 16 data points. What's 44 squared? Did somebody get that? All right, so this 1,936 divided by 16 gives us what? 120 what? 121. That's getting a little unruly there. All right, so we have 140 minus 121, 19, which is our sum of squares, right? Is that what everybody got? Okay, perfect. Yeah, there'll be a range of what you're allowed to. All right, so we have our sum of squares is 19. How do we find our variance again? Nope, not yet. Not the mean. N, yes, the number, right? So we take our sum of squares, we divide it by n, which gives us 19 divided by 16, which gives us what? 1.19 is our variance. And to get our standard deviation, we take the square root of the variance, which is the square root of 1.19. $1.09. Anybody have any questions about how we did that? No? Pretty straightforward? People feeling pretty good about it? Yes. Yep. Exactly. All right. So exactly, 44, 140, 19, 1.19, 1.09. So then the question was, what happens if we add 3 to every one of the data points and add 5? It doesn't do anything to the standard deviation, right? Because all we're doing is saying how far away from the mean come on now. All right, whatever. We're saying how far away from the mean is every individual data point. If you shift everything up 5, the distance between those hasn't changed. So again, if a constant is added to every score in a distribution, the standard deviation will not be changed. I won't ask you to do this because we're running out of time here. But does anyone have any guesses of what happens when you multiply? What's that? Yeah, what would it do to the standard deviation? Exactly. Sorry, this is throwing me off. I'm trying to hearing myself a half second after I say it. All right, guys, I'm zooming. Hold on. It should still be. Jesus.
Maybe you can just turn your volume down.
The volume's completely off. Yeah.
Oh, yeah, that might be.
But like, it shouldn't be coming through this computer at all because the volume's off. And so that, although I just turned it back on and turned it off again. All right. God. Like, there is no reason why that computer should be making a single sound, and yet it's still making sound. All right. So when you multiply these values, what you're actually doing is multiplying the distance. Right? Because you're not shifting the whole distribution up or down. You're multiplying every value. Right? So let's think about this conceptually. If I have one distribution here, let's say I take 0.1, it's value 1, and I take 0.5. These are just separated by 5, right? I mean, the range is 5. If I now multiply the whole thing by 5, that 1 times 5 is still 1. That 5 times 5 is now 25. So that range, that separation, is now 5 times as big. All right. So again, if you multiply by a constant, that standard deviation is multiplied by the same constant. Same thing with division, except in reverse. Now, why is standard deviation a useful measure, right? It tells us about the data, but it actually tells us more than you may realize about the actual spread. So when looking at a normally distributed variable, you have your mean right down the middle. And then with your standard deviations, you can have +1 standard deviation, +2 standard deviations, -1 standard deviation, -2 standard deviations. The distance between +1 standard deviation and -1 standard deviation encompasses 68% of a population. Right? So when we talk about IQ, for example, that is a normally distributed variable with a mean of 100 and a standard deviation of 15. And so that means 68% of the world's population has an IQ between 85 and 115. Now let's say everyone in here, because you all are geniuses, had an IQ of at least 130. Right? So 130 would be 2 standard deviations above. And 2 standard deviations encompasses 95% of the population, which means there's a remaining 2.5% in each tail. And so if your IQ is 130, you're smarter than 97.5% of the world. So think of this next time you see those stupid Facebook ads. You're like, only people with an IQ of 210 and above can solve this. Like, okay, there may have been a person ever who could possibly or conceivably get that, but.
So between,
Standard deviations?
yes,
Mm-hmm.
the first two that way is 68 and so on.
Yes, exactly. So between 1 plus or minus 1 standard deviation is 68%. Between plus and minus 2 standard deviations is 95%. Between plus and minus 3 standard deviations is 99.7%. So if you have a standard deviation, if you have an IQ of 115, you're at 1 standard deviation above the mean. What percentage of people is your IQ higher than? Why 75? Okay, so I see where you're coming from that. We're not doing the standard deviation isn't actually quartiles. So the quartiles would be the 25, 50, and 75%. But this standard deviation here is saying, okay, you're clearly smarter than the 50% below the mean, right? And between the mean and 1 standard deviation is 1/2 of this 68, right? So that would be an additional 34% on top of that 50%. So if you have an IQ at 1 standard deviation above the mean, your IQ is higher than 84% of the population. Does that make sense? All right. Let me All right, so here is our normal distribution. Our mean is right down the middle, right? And within every normal distribution, we can plot the standard deviations that we just calculated, right? So this is 1, this is 2, this is 3, this is -1, -2, -3. Below that mean in a normal distribution is 50%, right? Above that mean is also 50%. So if the question is, you have an IQ of 1 standard deviation above the mean, and we know that the distance between +1 and -1 is 68%, right, of the population. We know that if you split that into 2, so you're just getting the distance between there and there, that gives you 34%. The remaining 34% is there, right? And so if I say you've got 1 standard deviation, or your IQ is 1 standard deviation above the mean, that means you know your IQ is higher than everybody below that mean. And now you have to add that additional little bit there, which, as we know, is the 34%. So your IQ of 115 equals the 84th percentile. That make sense? All right. Other questions about what we've covered today? Oh, Savannah and Esther, have you been able to see the slides the whole time? I mean, can you see them now? Okay, good. All right. Any other questions about what we covered today?
Sorry, I still didn't catch on to what you just explained about how we got the 84%.
Okay. So let's try one more time here.
All right.
We've got our normal distribution, and we know that our mean is some value, right? And the mean is going to be right in the middle of a normal distribution.
Right.
So in this case, we know the mean for IQ is 100. That's just the raw score. We know that the difference between -1 standard deviation and +1 standard deviation is 68%.
Right.
So 68% of the distribution is going to have an IQ between 85 and 115. So if I say your IQ is 1 standard deviation above the mean, that means you've got an IQ of 115. We can plot that as the 1 standard deviation above. We know 1 standard deviation below the mean. Between these 2 points is 68%. And so what would half of that distance be?
That's 34.
Exactly, 34. And so that 34 means that because we're -1 standard deviation, we're 1 below and we're 1 above, that 34 represents the distance from each standard deviation to that mean.
Oh, okay, so you add that to the 50%, and that becomes
Exactly.
your 84. Okay.
Exactly. Yep. Yeah.
One way, we also make it easy to subtract the 68 from the 100, and then what's left over from that, we split that into 2. And that 16 is 1 tail, and the other 16 is the other tail.
Yeah. Yeah, absolutely. It's functionally doing the exact same thing. You're essentially saying, okay, what remains outside of here? Well, 68% is inside. You then have 32% on the outside, and you really only care about that. So you're adding that to that 68%. Yep. Other questions?
Excuse me.
Yeah.
I was gonna ask about the 115. So what's the point of it in the question?
So that's just your raw value, right? And so when we talk about people's IQ, the IQ measure is a 2 or 3 digit number that we assign people. And so 100 IQ is an average IQ. 115 corresponds to 1 standard deviation above that average, because a standard deviation for the IQ is 15. And so when you're adding, so you have that mean plus the standard deviation, or 100 plus the 15 was 115.
Oh, thank you.
Does that make sense?
Yeah.
Mm-hmm. And we use IQ because there are very few things in life that are normally distributed, but the way the IQ test is designed, it's normally distributed with a known mean and a known standard deviation, and so it makes it really easy to talk about some of these measures. All right. Well, I'll stick around if any of y'all have any questions. Otherwise, have a good weekend, and I will, what is today? Today's Wednesday. We won't have class on Monday, so I will see you next Wednesday.
I wanted to also ask about population and sample, because you were talking about that, and I'm not quite sure what the difference is, like between a
Between a
population
population
and a
and sample, give me
sample.
1 second. I'm going to try to here. All right. Can you hear me, Sonny?
Yeah.
One more time. Can you hear me, Sonny?
Yeah, I can hear you.
Perfect. So the population is everybody that you would be kind of extrapolating your data to. And so, you know, the population for IQ would be everybody that's alive. Population could also be, you know, everybody UAH. And so if I wanted to know if UAH students were smarter than UAB students, population would be all of UAH students and all of UAB students. But it doesn't, excuse me, it doesn't make sense for me to go out and get the 10,000 UAH students and the 20,000 UAB students to see who's smarter. Maybe I want to just get 50 of each. And so while the population would be all of the UAH students, all of the UAB students, my sample would just be what are those 50 students from UAH I collected and what are those 50 students from UAB that I collected. Does that make sense?
Yeah, okay, but like during the questions, you're like, is it population or sample? So it's like, which
So
is it gonna be differentiated if we're going to have to solve it?
yes, and so the question may be, what is the standard deviation for the population, or what is the standard deviation for the sample? But if you have the equation, you'll know which is which, because
Do they have?
by n for the population, and you divide by n minus 1 for the sample. Does that make sense? I'm sorry, I can't hear you, Sonny, if you're talking up. Sorry about that, Sonny. I think the Wi-Fi cut out for a second.
Yeah, William just explained. He's like, the sample would be n minus 1 and the population would be n.
Exactly. Yep.
But so it's gonna be there in the exam which one it is, because kind of, I think, because if it's not specified, how are we going to know which one to use?
Yeah, it'll be specified. It'll say find the standard deviation for the sample or find the standard deviation for this population. It'll say.
Thank you.
Of course.
And then just really quick, So about 68% of the scores will be within 1 standard deviation, and then it goes 95% and then 99.7.
Yes, exactly.
Okay.
So 99.7% of the population has a value between negative 3 standard deviations and positive 3 standard deviations.
Okay. And then we're gonna have to make sure we're pretty good on like our Greek symbols to know. I mean,
Yes.
at least for standard deviation, is it theta? Theta for standard deviation?
Standard deviation is sigma,
Sigma.
lowercase
Is
sigma.
it lowercase sigma? Okay. And then variance is.
Variance is just sigma squared.
Okay. Makes total sense.
Awesome.
Okay. Thank you.
Of course.
All right.
Questions?
The only thing I should do before every class.
The what? The health check? So UH has mandated that y'all do it at least every 3 days. They recommend you do it every day.
Oh,
But if you sign up for it, it'll send you a text if you don't do it every 3 days, and you can just quickly respond to the changes.
yeah, I just want to be prepared.
Yeah, no, I get it. It's a little tough getting in. It's a little confusing if you have to be getting tested and doing that. But yeah, you can do that every 3 days. And then I'll get a notification before class when everybody's already done it and is in compliance. And so that's why your name was there, because it said
Right.
you had.
Yeah, okay, thank you.
Of course.